Okay, so to refresh your memory, we're in chapter 11 and we're focusing on situations that have two populations. So we really only deal with three variables in this class, population variables. We have proportions, P, then we had means, mu, and then standard deviations. So in this chapter, we're dealing with two populations. And so because we have two populations, there are two general types of problems we're going to deal with. One is when the populations are dependent on each other, and the other is when the populations are independent of each other. So we have dependent and then independent. So 11.1 dealt with both of these in your book. So we have both of them. And there was a formula that was given. So we have a nice formula for the test statistic involving two population proportions that are independent. And then we have a formula for the dependent one. So this one was the one that was really weird. The absolute value of the difference between f sub 1, f sub 2 minus f sub 2, f sub 1. So that one goes there. So you just have to recognize it. The good news about it is kind of an easy one to spot when you're looking at your work. So we're going to move on to the mean ones. So we have two cases. 11.2 deals with dependent or dependent? Dependent samples. So 11.2 deals with dependent. So this one's 11.2 from your book, and then this one's 11.3. And this one is 11.4. And, well, I think they only deal with independent. We'll see. I think this book only deals with independent samples. 11.4. Okay. All right, so that's the general format of what's in your chapter. So we're going to move on to 11.2, the case of having two dependent samples. Two dependent populations. We're going to be making a statement about their mean. These are often called matched pair. Matched pair cases. They're matched pair cases because they're dependent. And so very often the reason they're dependent is because the subjects are somehow connected from one population to the other. And very often it's the same person. So the classic example you might have for a matched pair situation would be if I gave you guys a survey about math or what you thought about the school or something when you think of El Camino College at the beginning of the semester. And then now a semester later, now I give you guys the exact same survey. And so what I'm doing is trying to see if there's a difference between your responses at the beginning of the semester compared to the end after you've been in this class for 4 months, right? So maybe your opinion has changed or your attitude has changed or something, and maybe your results are different. But you guys are the same population for both surveys, so that's why it would be matched pair. Another sort of classic thing that we could do with this is maybe test your response, right? If we drop something and you, oh, wow, that was sad. If you do something like you're trying to catch a response, so maybe somebody else would drop it and you have to reach out and grab it and see how good you are at responding. We can match how good you are responding with your right hand versus your left hand, right? So you can see which one is better and which one is stronger, faster, more accurate. But you're still the same person. So we would do maybe population 1 would be everybody's right hand, the whole class. We have some sort of distribution of everyone's right hand. And then another distribution of everyone's left hand. But of course, there's a matched pairing that happens because you have one person, connected, left hand, right hand. So we would do matched pair. So you might want to look at the difference between your responses between your left hand and your right hand. So stuff like that. We'll see some examples in a little bit. But that's what we're dealing with. So when we deal with these two situations, what we will do is that we will subtract them. So let me show you what they look like. So another good news about this one is that they're very easy to spot because they usually give them to you in this kind of a format. Come on. this sort of a format. So here's that classic example about the dominance of one hand, your dominant hand. So I guess in this example you got to choose for yourself which one you consider to be your dominant hand. So we have a list of values, responses from each person. There were 12 people, and they did some sort of reaction time or some sort of exercise involving their dominant hand versus their non-dominant hand. So we see their response times for each person. So one person, person number 5, their dominant hand, they got this result for whatever test they did. And then their non-dominant hand, they got this result. So what we're looking at in every single one of these cases is the difference between them. We're going to subtract them, and we're going to get this list over here, which is the list of differences, right? And now the thing we're going to test in this case is always going to be that the difference is 0. We're going to test that as our null hypothesis. The difference is 0. Versus the alternative, which is going to be one of the usuals, not equal to, less than, or greater than. And that's going to be our test. Okay, so let's just jump to an example. So as you can see, they look a lot like this. About heights of fathers versus sons. Are the sons taller than fathers? So to test the belief that sons are taller than their fathers, a student randomly selects 13 fathers who have adult male children. She records the heights of both the father and the son in inches and obtains the following data. Are sons taller than their fathers? Use the alpha equals to 0.1 level of significance. That's kind of hard to read. Okay. So here's the data provided for us. We have 13 randomly selected members, fathers, and their sons. And then we got the heights of their fathers here at the top, and then the heights of their sons down at the bottom. And we want to test whether there's enough evidence based on this to indicate that the sons are taller than their fathers. What do you guys think? Raise your hand if you are taller than your father. No. Raise your hand if you're not taller than your father. You're shorter than your father. Okay, well, it's kind of hard to tell there. Well, the women, it's unfair to compare the women, right? The women with their fathers. We tend to have, men tend to be taller than women, usually, or more commonly. So maybe it would be fair to compare the women to their mothers, right? How many women are taller than their mothers? Okay. How many women are not taller than their mothers? Shorter than their mothers? Okay. So, it's kind of hard to tell based on that. Can we conclude anything from that? Well, that's where statistics comes in. So we have to get the numerical values, find the differences and all that. Okay, so let me copy that down. While I do that, put everything on your calculator. So go to list 1 and put all the values for the fathers on list 1. And then put all the values for the sons on list 2 while I copy this on the board. Yeah. Yes, you're going to have to sit over here on the side. So for those who came in late, I said you can take the retake today if you want to, or you can take it on Tuesday, your choice. If you want to do that, then you just come over here and do that now. Okay, so list 1 for all the father's information and list 2 for all the son's information. So, sons. I think that's right. Okay, so put on your list 1 here, list 1 and list 2, and what we want is to find the difference between them in a particular order. Now the order doesn't really matter, but you just have to keep track of what you did so that you can properly interpret the final information. So typically we just do the first one minus the second one, whatever you give. So we're going to find D, the difference between them. So D is going to be equal to the height of the fathers minus the height of the son. And so that for us will be list 3, which will be list 3, which is going to be equal to list 1 minus list 2. So we can find all these differences for them. Right? And once you do that, we're going to find the statistical information for D, which is going to be the difference between them. So if there is no difference between them, then as we do this, the average difference should be 0. Obviously, there's going to be some variation. Sometimes the father is taller, sometimes the son is taller. But if in general they tend to be the same height, then as we do this, like imagine I have 13,000 cases. Some of them I would have a positive number because the father is taller. Some of them would be a negative number because the son is taller. But on average, they should kind of cancel out. And so the mean of all of these should be 0 if in fact there is no real difference. But if there is a noticeable difference, like let's say the fathers tend to be taller, then we should have more numbers that are positive compared to negative. And so when I find the mean, then the mean might be shifted a little bit to the right because maybe the fathers are taller. Or the other way around, if the sons tend to be taller, then there'll be more negative values, bigger magnitude of negative values, and so the average of all of them might be skewed a little bit. Does that make sense? So that's what we're reaching for here. So find all these differences and then do a statistical analysis on those. Line disadvantage. Okay, another calculator. I will rely on you, awesome people. So like the first one is negative, right? The father is 70.3 inches. The son is 74.1 inches. Negative 3.8?
Yes.
Alright, well I'm not going to go through the whole thing, that's fine. So, go ahead and finish out all those guys there. And then we want to find the mean of the D's. So the mean, sample mean, but we put a little D there to indicate that we're talking about the differences. So X bar sub D. And then also we're going to find the standard deviation sub D. And what do we get?
Negative 0.315.
Negative 0.1, you said?
3154.
3154. Okay, and what about the standard deviation? Make sure you use S. This is the sample standard deviation, right?
2.89.
2.89.
71.
71. Okay. Good. Everybody's getting the same thing? Good. Questions? there's our sample information. So when we run into this, so what do we want to test? We wanted to test, are sons taller than their fathers? So we need to make hypothesis statement, right? So our hypothesis statement is going to involve means, the difference of means. So we want to state that the mean of the fathers is less than the difference in the fathers is less than the difference in the heights of the sons. So we want to test this. This is always going to be our null hypothesis. We don't really do anything different than that. That the mean of the differences, so really it's like maybe d bar. They use d bar as their notation, I think. I guess they don't put a d bar there. Oh, they put a d bar there. So just means of d. So that's going to be our null hypothesis that they are the same. There is no difference between them. Versus our alternative hypothesis, which is going to be that there is a difference. And so again, we have to choose between not equal to, less than, or greater than, just based on the word problem. And we were trying to test to see whether sons were taller. So if sons really are taller, just based on the way I wrote it here, then I would expect that the difference would be less than 0, would be negative. So we're really testing that one right there. So that's our null and alternative hypothesis involving the difference between fathers and sons. So this should have been really number 1 on our steps here, number 1. And then our sample information is probably number 2 here. Now that we have our sample mean, now this book actually uses this notation, d bar, instead of x bar sub d. I'm not sure what they use for x, s sub d. They do use s sub d. So so we have our information there, and also n is 13, so we have everything we need there. Okay. Next, we jump to our test statistic. Number 3 here is going to be our test statistic. And okay, so the formulas up to now we've been spending a lot of time making sure we understand where those formulas come from, but they get a little messy now. So we're going to spend too much time with these. The formula is given to you. It's going to be given to you on your formula sheet, and it is here. So here's your test statistic. Where'd it go? There it is. So our test statistic is going to be a T naught, which is d bar minus mu sub d, where mu sub d is this guy, which is our assumed null hypothesis, which is going to be 0 in our case. And then s sub d, which we found, and then square root of 13. So that's going to be our test statistic. Remember, the test statistic is the value that helps you figure out the probability of getting a sample like this under the null hypothesis. So test statistic is going to be d bar minus mu sub d divided by s sub d all over the square root of n. And notice that this is a t sub naught, right? So it's a t distribution as opposed to a z distribution or a chi-square distribution. So we can calculate it now. T sub naught is going to be equal to this number, negative 0.13154 minus 0, since this thing is 0. So usually, sometimes that's just omitted. 2.8971 divided by the square root of 13. So what do we get?
Negative 0.1637.
1 point?
Negative 0.1637.
Okay, so negative 0.1637. Yes, everybody else got that? Okay, so what does that mean? It is a value in a t-distribution with 12 degrees of freedom, and we can use it to determine the p-value. Well, I'll write it over here. So we have something that looks like this. This is a t-distribution with degrees of freedom equal to 12, which means the mean is 0, sigma equals to 1. And this guy here is this number over here, negative 0.1637, and we want to find this, the likelihood that we would get an example like this or farther to the left. We know to the left because of this guy, but usually it's more extreme anyway, so it's because of that. So I want to find that. That's going to be my p-value. Yeah.
Why is it 0 and 1? Isn't it?
It's the standard t-distribution. That's what this thing automatically gives you. Right? Just like when you have z-naught, the other test statistic, it automatically gives you z. So this has already been quote-unquote standardized. Notice that it's the value minus its mean divided by its standard deviation. So that's kind of like the z-score, but now we're getting a t-score out of it. So it's the standard t-distribution. Yeah.
The mean is wrong. It's 3154, not 3154.
Yeah.
Oh, wait, what? Where?
3154. There's no
3, 1 here?
54, yeah.
It's no, there's no 1 there?
No.
Oh, there's no 1 here, guys?
So the answer should be
Yeah.
negative 0.3154.
Okay, alright, so that guy's there, so there's no 1. And so the whole answer over here is different then?
Yeah.
What's the answer? Is it still negative? Negative what?
3154, 0.3154.
3,
No,
One.
negative 0.3154.
oh, 0.3154?
Yeah.
Is that what everyone's getting now? We're good? 0.3154? Don't make it without a calculator. Alright, I'm at your mercy. Negative 0.3154. Okay, so in the prior ones, remember in the other ones where I would like push this whole thing to the side and we'd spend about 40 minutes trying to figure out where this formula came from, and then you would all hate me and I go, oh, you don't have to write any of that because that was just to show you where the test statistic came from, the formula. Well, I didn't really do that this time, so that's why we're just going to rely on the test statistic. So the test statistic automatically gives you the value in the standard t-distribution, the standard normal distribution, or the chi-squared value that you need in order to figure out the probability, the likelihood of getting this result, this sample result under this null hypothesis that the difference really is 0. Okay, so I didn't spend much time with it, but you might recognize this as the mean, the sample value, the sample mean minus the population mean divided by the standard deviation. So this should look a lot like the work we did in chapter 8 with sampling distributions of means, which is where this really comes from. Okay. Yeah. Another mistake?
No, the result, that 3154 is fine there, but the result is negative 0.3925. The result of the t,
Yeah.
that there.
So 0.3.
3925.
925.
Yes.
925. We're good?
Yeah, it was just a. It was
Yeah,
just
just trying to make it look bad on TV, huh? So we're good now? Can we get some consensus? Everybody's agreed, this is good. Everything's good here. This is the right number there, and this is the right number here. Alright. 0.3925. Okay, so if that's right, then this guy will tell you the p-value. That's our next step, right? So step number 1, null hypothesis. Step number 2, deal with your sample information. So in this case, list 1, list 2, list 3, you're going to do the subtractions, right? You don't want to do this by hand. That's ugly. So you got to make sure you know how to do that with your calculator. It'll save you a lot of time. Then do a one variable statistic so you can find the sample mean and the sample standard deviation of the differences. Keep track of which one was which so that you know whether you want it to be positive or negative based on what you want to conclude. Number 3 is to go to your test statistic. This guy you don't have to memorize. It'll be in your formula sheet. You just have to figure out which formula applies when in which situation. So you just have to pick it out of the lineup and use it. It's that one. Then you find your test statistic. There you go. Then you draw a picture based on whether it's a t-distribution, a z, which would be a normal distribution, or a chi-squared. Draw your picture. Make sure you label it. These formulas always give you the t-distribution and the normal distribution as the standard ones. So these are always 0, 1 for those cases. So that makes that easy. And then this is the test statistic there. So we just got to find that area there, which is our next step, step number 4. Find the p-value. So the p-value in this case is going to be the probability. So this is a little t naught there. So the probability that t is less than negative 0.3925 is going to be TCDF from negative infinity up through negative 0.3925. And now the calculator only works when we're dealing with the standard t-distribution. So you don't even have to tell it the mean and the standard deviation. All it cares about next is degrees of freedom. Okay, so lower bound, lower, upper, and then degrees of freedom. That's what you type in your calculator. And what do we get? 0.
0.3508.
3508.
Yes.
Do we have some consensus now? 35%. That's pretty big, right? That's not unusual. This is letting me know that a result like this one, this result, is not that unusual under the assumption that the difference really is 0, right? If the difference really was something negative, we should have gotten a result that's a little bit farther out. It's not that unlikely that we would get a result like that one based on 13 values selected from a population that has a mean of 0. Okay, so we just don't have enough evidence to conclude that sons really are taller than their fathers based on these 13 values. Okay? So that's the 5th thing, our little conclusion. So because the p-value, the probability of getting a result like this one, under the assumption the null hypothesis is true, is way bigger than alpha. So alpha will be given, very often they use 5, right? It's a very standard value to use. And they said, oh, here we're using 10%, the 10% level of significance. So even though it's bigger, 10 is still way smaller than this, less than 0.10 equal to alpha. So because that's way bigger than that, we fail to reject the null hypothesis. Fail to reject the null hypothesis. We fail to reject it. We're not saying it's true. That's not saying we conclude that it's absolutely true. The difference is 0. You know, we are opening the possibility that maybe it is false, but you know, we just got 13 values here, and maybe just based on these 13 values, I don't have enough evidence to say that this thing is wrong, so we leave it alone. But maybe if I went out in the world and I took a larger sample, maybe at some point there will be enough evidence to conclude that that thing is wrong. But for now, by default, we go, there's not enough evidence. We fail to reject the null hypothesis. There is not enough statistical evidence to support the notion that sons are taller than their fathers. Good. Questions, comments, issues? No? 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 Good? 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 Okay, so that's an example using the differences. There's only one more here, which is going to be 2 population means where we're looking at we're testing whether the mean of the 2 populations is the same or different. So the null hypothesis is always going to be for us that they're the same. So here's our possible values. Same thing for the alternative hypothesis, that either not equal to, less than, or greater than. And then we have our test statistic. Again, I'm not going to spend as much time as I did before trying to show you where that comes from. but it should look familiar again. So again, we're going to look at the difference between the samples and the difference between the means, the population means. And then the standard deviation might look a little weird where they get that from, but it's just beyond the scope of this class to get into that. But that's our test statistic. So let's look at one. So how about male versus female reaction times? This is number 14. Researchers at the University of Mississippi wanted to determine whether the reaction time in seconds of males differed from the females to a go-no-go stimulus. The researchers randomly selected 20 females and 15 males to participate in the study. The go-no-go stimulus requires the students to respond to a particular stimulus and not to respond to another stimulus. The results are as follows. Okay, so we have a nice big table of values that belong to the females participating and the males participating. So is it clear why in this case these are independent compared to these where they were dependent? Right here they're dependent because obviously we want to compare each father to their own sons. It really wouldn't make much sense if I just took the average of all of these, the average height of all the fathers and the average height of all the sons, and subtracted those two things. Then we would be missing something, right? We really want to know the relationship between them. So that's why it's important to kind of match them up, father to son, find the difference of each one individually, and then we want to look at the average of the differences once they've already been kind of matched up. Whereas here, now we have a situation where we have two separate populations, the women and the men, and there isn't necessarily any connection. Now, if it turns out that we're looking at like brothers and sisters, then maybe it would be a matched pair situation again, because they're related, so maybe reaction times might be connected, or some other connection between the male and the female students. Like maybe we picked, people from particular groups, like maybe the basketball team, we picked a female from the female basketball team, the women's basketball team, and a male basketball team person, and we looked at their reaction times, and we compared the male and female, and then maybe we took a different sport, maybe we went to the bowling team, we took a woman from the bowling team, a man from the bowling team, and that might be a matched pair situation, but not in this case, right? Is that clear? Two different populations. Okay, so what we want to do is notice that, look at it for a second. So we have two different parent populations, population number 1, population number 2. They have a certain mean, a certain standard deviation, a certain mean, and a certain standard deviation. So for our purposes, we're going to assume the null hypothesis is going to be that, well, okay, so, how do you label each one? So we put a little 1 underneath there and a little 2 there, to show you population 1 versus population 2. And what we want to compare is the differences between them. So we want to say that if we take some samples from here and some samples from there, and we get those two sample means, and we subtract those two sample means, and look at the difference between each one of them and graph them, we'll get some sort of a distribution that will also be normally distributed under certain kinds of conditions. That's really the basis of this test, which is all kind of brought together or kind of summarized here. So let's look at the test requirements. So to test hypothesis regarding test hypothesis regarding two populations means, mu1 and mu2, with unknown population standard deviations, we can use the following steps provided that, so the samples are obtained using a simple random sampling through the random, okay, so that's standard, that the samples themselves are random. The samples must be independent, right? We're independent, two populations are independent section. The populations from which the samples are drawn are either normally distributed or the sample sizes are greater than 30. That's standard, as we've seen before. For each sample, the sample size is no more than 5% of the population size. So just your standard kind of requirements that we've been working with before. So as long as those have been satisfied, then we'll be guaranteed that the resulting distribution will look like this. So, in other words, we take a sample from here, n sub, let's say we take a sample of size 17 from there. So the first guy here is going to have some sort of sample mean. I'll connect it to the first one. I'm just making up some numbers here to show you my point here. So let's say the sample mean here is 13. Sample standard deviation from it also is given, so maybe it's like a 2.1 or something like that. Then another sample over here from this one, so maybe this one is, I don't know, 15, and S of 1 is, I don't know, 3.2, and so on. So we take samples from this thing over here. We also take samples from this guy. Now the sample sizes could be different, maybe 23. So 17 from there, 23 from here. There's also sample means for each one of these. So the first sample maybe has a sample mean of, I don't know, how about 28 with S equal to 2.1. Maybe the second one has a sample mean of 21 with S equal to 1.7, and so on and so forth, right? So that's what's happening. We have a population of some kind. We take samples of particular size. Another population with a particular samples of a particular size are being drawn. So what we're going to do is that for each one of these, we're going to subtract them. So we're going to look at x bar 1 minus x bar 2. Look at that difference between them. In my little made-up example, that would be like 13 minus 28. In this case, it would be negative. And we do that for each one of these. Bar 1 minus x bar 2. So in my little case here, this would be like 13 minus 28. And then over here, in this case over here, we would have a 15 minus 21, and so on and so forth. So what this is saying is that if I look at these results, let's go ahead and do it. So this is equal to negative 15, this is equal to negative 6, and so on and so forth. So if I graph these results here, all these differences, that difference will be a normal distribution. And that this guy right here, the mean of this distribution, mu of it, is going to be equal to mu sub 1 minus mu sub 2. And that the difference between them, the standard deviation, well, that's the tricky part. So we are going to make an assumption that these two are equal to each other. Even though we don't know what they are, we're going to assume that they equal each other. So sigma 1 and sigma sub 2 are equal to each other even though they're unknown. I don't know what they are, but we're just going to assume that they equal each other. And that standard deviation is a little on the mysterious side here. It's going to be equal to sigma sub 1 over n1 plus sigma sub 2 over n sub 2 squared, and then square root of that whole thing. Okay. Where did that formula come from? Like I said, it's a little beyond the scope of this class, and we're just going to have to deal with it, but that's what it is. Okay? So in a case like this, then when we have a particular number, so what's going to happen is that we are going to be given one particular sample from this population, one particular sample from this population. We're going to look at its mean difference, and that's going to be one little dot in this guy. Right? So it's very similar to what we've done before. So for us, we will be given something here. Some x, this guy will be given. And some other value over here will be given. And we're going to look at the difference that we get. This is our result. And that'll be a little dot over here somewhere. So we're going to want to find that area over there. How do we find that area? Well, for us, under the null hypothesis, we're going to assume that this is equal to 0. Right? The null hypothesis is going to be always, for us, that these two things were equal to each other. That's the only thing we can test here. So it'll make it easy for us to quote-unquote standardize it. Remember how we standardize things? We take the mean, our sample value minus its mean divided by its standard deviation to kind of get that sort of z-score or t-score. And that's where this formula comes from right there. So notice our test statistic, t sub naught, is equal to x bar 1 minus x bar 2. This is our sample result. That's going to be one of these little dots here. Minus the mean of 1 minus mu of 2. Well, that's because of this guy. So this is the mean of this distribution. divided by the square root of, well, since we don't know what sigma is, our best choice is to use our sample standard deviation, which is why we have to deal with t's. Remember that whenever we substitute the sigma with an s from our sample, we have to change it from a normal to a t-value one, right? If this was a question where they told us this, we knew these guys, then this would be a z-value instead of a t-value, right? But because we're making an assumption, we jump to that. And then for us in this class, this guy is always 0. So the formula gets even nicer than that. Is that okay? All right, so I was just trying to give you a little bit of like background as to where that guy came from. It looks familiar. It looks like a lot of the other stuff we've done, but I didn't really give you like really great detail on it. So just to kind of give you some intuition as to where that comes from. But now let's do one, and I'll show you what you need to write down on an actual like question on the class. So let's go back to the reaction times question. So they were measuring reaction times between males and females. So they gave us a nice big table value. Guess what you're going to have to do with all those numbers? Plug them into your calculator so you can find the information from each one of them. So the mean and standard deviation for each one. So step number 1, we're going to put our null hypothesis. Our null hypothesis is always going to be that the populations equal to each other. Do they like 1 equals mu sub 2? So that's our null hypothesis. It can also be stated this way: mu sub 1 minus mu sub 2 equals 0. Right? So if they equal each other, then the differences equal 0. And the alternative hypothesis is going to be, well, it depends. It could be your standard not equal to, less than, so not equal to, less than, greater than kind of deal. And what did they want here? As you're doing that, how many values, right, do we have for each of these? We have our sample information. So we have for population 1, population 2, we have n equals to 20 for the females.
Yeah.
I'll put females here. Males. Okay, and so n equals to 15. The conditions for this whole thing to work required what? Greater than 30, or that the parent distribution be normal. Well, they didn't say that the parent distribution was normal. They didn't say the reaction time of female students for the entire population is normal. They just gave you this result. And since the samples are less than 30, well, we just have to double check that this comes from a population that's approximately normal. So how do we do that? Remember the normality test on your calculator? You got to do that thing where the dots and you see if it's approximately linear. So you got to go to y. So you got to go to your distributions. Oops, sorry, not your plots, and it's the last graph on the right. And then I think it just asks you for the list, and then you graph it. And so it should be something. Remember, it looks like this. It's like. Actually, no, it goes through the center. Should be a bunch of dots, I think, that kind of look like that. Hopefully, these things look approximately linear. If they look approximately linear, then we are fairly confident that the results come from a normal distribution. Remember the ones that are really nice that the book had also threw in these lines. It had like these lines like that, so you can kind of judge whether or not they are within the boundary. But our TI calculators don't include those boundaries, so keep that in mind. I wouldn't give you something on the test that doesn't work, though. That would be kind of cruel, I think, for me to give you this whole thing and you spent a long time doing this whole thing, and then the answer was there was no solution because this was not normal. Oh, that would be mean, I think. But anyway, so just keep in mind that you should, if you're going to do this in real life, you've got to keep that condition in mind that it works. So the sample sizes have to be greater than 30, or then you have to do a normality plot to be convinced that perhaps this data does come or is likely to come from a normal distribution. Good. All right, so hopefully you're done now. Did people get the sample and mean information for these guys? I mean, the sample and standard deviations for females? Anybody?
0.4574.
I'm sorry, what are we doing? The means of the females?
Yeah.
Okay, what is it?
0.474. 4574.
4574. Everyone concur? That's what are you getting? Yes? No. 79? 9? Okay. What about S then? What is S? 1.2?
0.1226.
1226.
Yeah.
So 1226, good. Okay, what about the male? What's the mean of the males? .4317. And what about S of the males?
0.1246.
Okay, we're good? Okay, so null hypothesis, we got it. That one's easy because it's always the same. So our null hypothesis is that the two populations are going to be equal, which means that when we subtract them, it's 0. That's always the case for us in this class. The alternative hypothesis now is based on the information, and it says, is there enough evidence to indicate that there's a difference between them? Right? It says, test whether there is a difference in the reaction time of the male and females. So we want to go with not equal to, right? Test if there is a difference in either direction. So this one's a not equal to, which means that if I subtract them, then we just want to say that they're not equal to 0. Good. Okay, so now we got all our sample information. Next, we go to our test statistic. So 3, our test statistic, which is T naught equals to the difference between these. Oops, I should have put a little 1 here to indicate that all of these are the values from population 1, and a little 2 there to indicate that these are all the values from population number 2. So the test statistic is going to be x sub 1 minus x sub 2 bar. So the difference between the means in our particular sample minus mu sub 1 minus mu sub 2 divided by s sub 1 squared over n1 plus s sub 2 squared over n2, and then the square root of all that. And like I said, for us, this is always 0. Right? Because we always test that the populations are equal to each other, that the mean of both populations are equal to each other. So we have everything we need to come up with our test statistic. It's going to be 0.4579 minus 0.4317 divided by 0.1226 squared over 20 plus 0.1246 squared over 15, and then we want the square root of that whole thing. So that's kind of ugly. worthy of this calculator.
What's the best way to put that into the calculator?
Yeah, yeah, I mean, I would start with the denominator. Start here and find this, square this, get an answer, divide it by 20, get an answer, add the previous, right? You do previous answer plus, and then try and do this in its own parentheses, get an answer. So in little stages, I guess, is how I would do it. But this is the hard part. So if you can maybe find whatever this is and write it down, find out what that is, and then separately find out what that is. You might want to write it down and then add them together. If you at least do that, it might simplify life. But this is, a challenging thing to type all into a calculator. Unless we have, one of the cool calculators that lets you just type it all in, like this one. So 0.4579 minus 0.4317. So as far as the test goes, this is commonly a place where a mistake is made. That's why it's important for you to write this down so that this is your step. I know that this is your step. Even if you give me something that's wrong afterwards, I'll know it's a simple calculation error. And yes, I'll take off a little bit, but it'll be a little bit compared to you gave me some weird number, you never wrote this down, and I have no idea where you got that number from. Well, I'll just assume you have no idea what you're doing. So make sure you write this down, and then even if you make a calculation error, it'll be a small error, and then I'll just proceed from there. Okay, well, you messed that up. As long as it's somewhat reasonable, then I'll move on and continue the problem under the assumption that that was the correct one. This calculator is cool like that. It lets you type it all in, all neat like that. But like I said, so don't stress too much out about that. So make sure you write down this guy right here on your test. That way, even if you get something a little bit off, as long as it's a reasonable answer, I'll just assume, oh, okay, just a small little calculation error, and then I'll move on from there that way. So I'm getting this 0.619. 61986. Okay, so that rounds to 61.99, I guess. We'll go with 99. 61.99. Good. People are sort of getting that. Depending on how you do it, if you end up getting this as an answer and writing it down, you're probably going to truncate it a little bit, rounding, and then same with here, and then you round it again, and then you add them, and then you take the square root. So if you do too much rounding in the middle of calculating it, then you end up with something that's a little bit off. So that could be the reason. So again, just write down what you did. Try not to do too much rounding in the middle of your calculation, and ultimately you'll get to your answer. Good. Okay, so remember the test statistic is the value in a t-distribution that will give you the result you want. But something should be weird now, because now when we go over here and draw this, we do this. Okay, so this is the standard t-distribution. But what do we do with degrees of freedom? Okay. So it says it right here. P-value using the smaller of the n-1 or the n-2. Okay. So remember, degrees of freedom was always n-1, but now we have two different populations, so which one do we use? Well, we go with the smallest one. So degrees of freedom for this one, n minus 1, this one be degrees of freedom equals to 19. This is degrees of freedom equals to 14. We go with the smallest one. So that's what we're going to use over here. Degrees of freedom equals to 14. Remember, this is the standard t distribution, so mu is 0, sigma is 1, and then we have this thing. So this guy's positive, it's over here. It's going to be 0.6199. And so we get something that looks like this. Okay. However, we were testing not equal to. So we have to think about the other extreme. In this extreme, we got a positive because in this particular example, it turned out that that one was bigger than that one. So when I subtracted it, it gave me a positive. However, we want to test the possibility, the likelihood that in another example, I might get the opposite, where this one would be smaller and this one would be bigger. So we have to test the other side as well, which means we got to come over here and find the area of this side as well. Well, t-distributions have that nice symmetry anyway, so I know that that side over there is going to be negative 0.6199. So when I find the p-value, really what I can do is just find one side and double it. Okay, so you just have to be careful or remember to double this. Number 5, the p-value is going to be the probability that t naught or t is less than negative 0.6199 or t is greater than positive 6.199, which is going to be equal to twice the probability that t is greater than 0.6199. Right, just pick one of them, it doesn't matter, and double it. And so in our case, that means that there's going to be 2 times TCDF from 0.6199 up to infinity with degrees of freedom equal to 14. I'm getting 27.26 for this guy. So 2 times 27.26. So when we multiply by 2, we get 54. 0.5453. Oh, it's like ridiculously off. You guys sure you guys got the right numbers over there? It's a really big probability. Usually they're kind of small. So I'm a little hesitant that that's the right answer just because of that. So this looks correct since it's really close to 0. And it's not even, it's like a little bit more than half the standard deviation. So it's definitely really close to 0. That means the reds are going to be very big. So that looks accurate. So just making sure that this part over here was accurate. But if it is, then that's the answer. So this is telling me that the likelihood of getting a result like this, very common. Very, very common. Almost a 50% chance, 50-50 chance of getting a result like this under the null hypothesis, where the null hypothesis is that the populations are equal to each other. Right? And well, that makes sense. Look at how close these two things are. Do we have any evidence that the reaction times are different from males and females when the average reaction time of the female and the average reaction time of the males were so close in our sample? Like they're almost identical. So clearly we just don't have enough evidence based on those samples to conclude that the null hypothesis is not true. Good. So that's our conclusion. That's the last thing that's missing. Conclusion. So I want to say that number 5, the conclusion. So our p-value was equal to 0.5453, which is way bigger than the alpha value given. Alpha value in this case was 5. So definitely way bigger than 5%. Right, so the probability is very, very big, way bigger than the alpha equals to 0.05%. So we fail to reject the null. There is not enough statistical evidence to indicate that the reaction time between males and females is different. Yeah, question?
When you calculate p-value, how do you do the degree of freedom when you have 2 samples?
Yeah. So when we have 2 samples, right? The female one had a sample size of 20, which would have been 19 for degrees of freedom, and the male one had 14. So we go with the smallest one. That's the deal. So whichever one is the smallest of the 2, that's the one we use. Okay. Good. Good. There's a more complicated formula out there that I don't know if the book has. There's a more complicated formula out there to kind of get a more accurate answer. But this is good enough for us. So this is kind of like the quick and dirty way of doing it, and you get a pretty good answer anyway. Good. Any questions, comments? No. Okay. So that concludes this guy, which is 11.3. Inference about some standard deviations. I know you guys are going to be very upset by this, but I think I'm just going to skip 11.4 and stop there. I feel like you have enough.
Upset.
I know, no writing, please.